Now we're going to continue the topic of finding all of the real zeros, but we're going to look at some ones that you can't find through factoring. So basically that just means we'll have to use the quadratic formula to find some of our solutions. So these examples are going to be similar to, but slightly more complicated than the last ones we did. We're going to look at an example of a polynomial with a degree of 3 and a polynomial with a degree of 4. As a reminder, the degree is just the biggest exponent you see on the variable. So if the biggest thing you see is an x cubed, that's going to be what this first bullet's about. If the biggest exponent you see is an x to the 4th power, then we'll be using this second bullet. So we're still going to make our list of possible zeros, and then we're going to test numbers from that list using synthetic division until we get one that works. As soon as we find one that works, usually we want to try to factor it, but today's examples will be a little bit more complicated, so we're going to end up having to use a quadratic formula on whatever's left from the synthetic division, that breakdown you made. The degree 4 example is even more complicated because after we make our list of possible zeros, we will actually have to break the polynomial down twice by using synthetic division. Once we have found 2 solutions using synthetic division, then we will switch to either factoring or the quadratic formula to find the remaining 2 answers. So in this example, the most important thing to highlight from the question, it does not just say find the possible zeros, it says find all the zeros. So we still need to start off by listing out the possible ones, which means my factors of the last number, so 1 and 3. And then the factors of the first number, since this is just a 1 for the leading coefficient, that means all we have to worry about is 1 over 1 and 3 over 1. So that's our list of possible roots, but we need to know which ones actually work. So the idea here is that we need to start testing the values one at a time using synthetic division. Now, as a shortcut, you can use the remainder theorem to kind of get an idea of whether a number will work before you go through the process of plugging it in. For example, I don't think plugging 1 in is going to work because I can visualize 1 cubed plus 7 times 1 squared plus 11 times 1 minus 3. If I plugged 1 in, I know this would be 1 plus 7 plus 11. If you subtract 3 from that, that's not going to equal 0. So I'm using the remainder theorem, the factor theorem, to identify that 1 is not worth trying to plug in. Similarly, you could use that process to eliminate positive 3 as one of the numbers to even bother checking, because 3 cubed plus 7 times 3 squared plus 11 times 3 minus 3, even without computing it out precisely, you should be able to tell that that's a huge positive number. We're looking for a number that will equal 0 when we plug it in, so I know that 3 is probably not worth the time of using synthetic division on either. So really, I'm just going to be interested in -1 and -3, and I'm going to go ahead and start off with testing -3 as the value. So -3 is one of the list of possible zeros, and the coefficients of my polynomial are 1, 7, 11, and -3. So we add the numbers in the column. There's just the one number here, so the first one comes straight down. Then you multiply by what's in the box, and then you add the column again, multiply by the box, add the column, multiply by the box, and add the column. So what we have just found is since -3 is a factor, that means I can write this as x plus 3, because if you set this factor equal to 0 and solve, that's what would give you an answer of -3. So -3 is an answer we just said. And based on what's underneath the synthetic division, that means I have x squared plus 4x minus 1 for what's left after we take the x plus 3 factor out. Now, usually you would try to factor this to get the other answers, but in today's examples, we're doing some slightly more complicated ones. So if you cannot factor, or if it just seems very hard to factor, we're going to be switching to using the quadratic formula instead. So now I'm going to write x equals -b plus or minus the square root of b squared is 16. And then be careful with the signs on this. I see a lot of mistakes made here. It's minus 4ac. I think it helps to carefully use parentheses so that you don't lose track of which numbers are positive and negative, because now I can see what's happening as a -4 times a -1 will actually be a +4 in there, all over 2 times a, which is just 2. If we simplify this a little bit, we have -4 on top. Inside the square root, now we're doing 16 plus 4. And the square root of 20 can be broken down. Remember, you can use a factor tree to simplify this, or if you recognize that 20 is 4 times 5, and 4 is a perfect square, it ends up being 2 root 5. And then the last simplifying step we can make here is recognizing that all of our terms on top are divisible by 2. So since we have everything divisible by 2, we can just divide each term by 2 to leave this instead as -2 plus or minus root 5. So altogether, our answers are the -2 plus or minus root 5 and the one we found from synthetic division earlier. Don't forget about that one. So we actually have 3 solutions, and that's these 3 numbers right here. So now here's an even more complicated example, because this one is starting with an x to the 4th power. So this is what the second bullet was talking about, where we're going to need to find 2 answers that work using synthetic division. Now, the process of setting up your possible roots, it's all the same. So just to save a little bit of time, I went ahead and listed them out. I have the factors of 8 on top, the factors of 2 on the bottom, and then I created every fraction by going 1 over 1, 1 over 2, 2 over 1, 2 over 2, 4 over 1, 4 over 2, and 8 over 1, 8 over 2. But a lot of those numbers were duplicates, so these are all that were left after I simplified those. To test values, I'm going to start off using the number 4. And then remember, you can kind of get a better idea of which numbers will work ahead of time if you just see if you can plug them in for x. We want one that would end up equaling 0. So if you can do those computations mentally, sometimes that saves time and helps you narrow down the list of possible roots first. So if I use the number 4, I have the coefficients 2, -7, -8, 14, and 8. Well, the first number comes down, and then we just go through our same process of multiplying and adding. And we're looking for ones that give us a 0 here. So now my polynomial is broken down. I could write this as x minus 4 and 2x cubed plus x squared minus 4x minus 2. But that's not small enough yet because we still said that we're starting off with an x cubed term, which means we need to find another number using synthetic division that will work before we can get our final answer here. So basically we need this piece underneath to be down to just 3 numbers, not 4 numbers like what I have here. So I'm going to pick another number from the list. This time I'm going to use -1/2. It's always painful when you have a fraction one that you have to do, but I figured I'd show you as an example in case this comes up for you as well. So the first number comes down. -1/2 times 2 is -1. These add up to give me 0. Multiplying by 0 is the same thing. And then -1/2 of -4 is +2. So that's my second solution that worked. So now I can break this expression down as x minus 4. And then this piece here is x plus 1/2. Although that could be written another way as well. If you doubled both of these terms in here, it would instead say 2x plus 1. That's the same thing. So you could write 2x plus 1 if you would rather. Either way, you get the solution of -1/2 from that piece. And then the rest of what I have is 2x squared. There's a 0x term, and then -4. So after finding the first 2 solutions from synthetic division, now I have a polynomial where the biggest exponent is an x squared. So now we can solve this normally. Sometimes it's factorable, sometimes it's solvable. In this case, I can actually just write 2x squared minus 4 equals 0, and then finish solving it from there. So luckily, this particular example did not require the quadratic formula again. I'm just going to be doing opposite operations. So if I add 4 to the opposite side, divide by 2, and then don't forget, when you take the square root of both sides of an equation, you get a positive and a negative answer, which means our 4 zeros altogether are 4, -1/2, and plus or minus square root of 2. And remember that the number of answers you have should match the biggest exponent you have in the polynomial. So the fact that I have 4 answers agrees with the fact that my biggest exponent was a 4. So that's all for the notes on this topic. Tomorrow we'll be looking at finding answers that have imaginary numbers in them.